Hello everyone, this is Clara Godoy. I'm here with Ronald Siat.
Hi, hello.
We're here to continue the brief introductory course of CivilFEM powered by Marc. Remember that you can comment this webinar using the Twitter hashtag CivilFEM course. And now we're going to start with the set exercise we had gave you to try at home in the first part of the course. Remember that it's a 2D linear static analysis of a dam, which is submitted to hydrostatic pressure, and we have to obtain displacements and stresses in the dam and soil terrain. So now we go to CivilFEM. Remember, it's a 2D static structural model.
So first, the definition of the geometry. As you have seen in the last webinar, we can use the grid just by picking or just setting directly the coordinates using the properties window. We will define all the points, and then we will create the surfaces joining all the points defined. We will define the point for the terrain and then the point for the dam. It's very easy. You have the all the coordinates in the statement. Just you have to follow the statement and insert all the coordinates. As we only are working in a 2D dimensions, we just have x and y as the third coordinate, the z won't exist. We are using the default unit system, so all the dimensions are in meters.
And now the last point. Okay. So we can see that point it's not correct because I missed that sign. And now we have all the points created, and we only have to create lines to each point. We join them as we see the last time. You can pick them and create several lines by using Control Enter or by clicking here in OK and New. It's faster using the Control Enter, pressing Control Enter. And once we have all our lines created, we only need to fill that lines with the polyline surface bar curves. We select all the lines and we have here our terrain. And now we're going to select the other ones and we have here our dam. The next step is to create the material. In the statement we have that is concrete of Eurocoat. And now we need to create the rock that is igneous growth, is a rock, is a granite. And now we have all we need to create the solid structural element. We are going to set here the name. And now we choose the geometry. And we have to change the mesh control. We're going to select quadrangle element type and 4 meters of edge size. And now we have to create the other solid. We're going to call it dam, and we select the geometry and change again the mesh control to quadrangle and 4 meters.
Always take into account the limit of number of elements for a student version, but in this case there are just not less than 800 elements, so we don't have any problem in that.
As we have done the geometry shared by the two surfaces, you can see here how the nodes in this part are the same, and we have an homogeneous mess. So now it's time to create the loads. We're going to create a new load group, and we're going to create two linear loads, one in that direction from that load. And now we're going to choose the line where we want to be, when we want it to be applied. We select by picking, and now we choose the line. As is an hydrostatic load, we have to put one of the ends at 0, but not this one.
Yeah, the I and J ends are defined according to the direction of the line. If the line is, in this case, the line was created from top to bottom. That's why the Y is at the bottom.
And now here you can see how the hydrostatic load is created. Another one is from that structural element, the same value, but now is applied in Y negative direction, and we need to change again in the same way the load where is the line where it's applied.
In this case, it's a constant linear pressure.
And now the boundary conditions. These times are linear boundary conditions in that structural element, and in this line we have to constrain the movements in X direction, and we need to do the same in, again, that structural element and that curve, but this time in Y, and again the same structural element and this curve in X direction again. Now we create the load case, and we add the load, the hydrostatic load, and the boundary condition, and we solve our model to get the results. Now if we plot the results of displacement, we can see how the hydrostatic load push the dam, and in the stress results we can see how in the
Upstream, or the downstream, we can see in upstream and downstream areas the stress concentrations. Okay, so let's continue with our following exercise. The following exercise just the creation of captured cross-section is a generic cross-section. This cross-section will be used to mesh beam elements. The particular thing in this case is that this is not a typical cross-section which is defined in the library, and we will create it just by using the 2D modeling. In a 3D analysis, but we will create for this particular cross-section we have to use local X and Y model definition or geometry, and then capture this section in this coordinate system to use it to mesh beam elements align. So I will create it. This here you can see the dimensions of this this cross section of this slab bridge, voided slab bridge with three holes. I will create just well, a kind of a short version of this, not following the same dimension, just to show you how to define a capture sections, a capture section for a concrete cross section. So if I open a new analysis, the model is already, in this case it's a 3D static analysis, and we will create our geometry. First we will activate our grid. Make sure that you will use the X and Y plane to capture our section. We need this plane to be used as a model geometry definition. So I want to change the size of my grid because it's too big. Yes, I need 20 meters, and I will reduce my spacing as well to 25 centimeters. Now I can create my geometry. For example, I will create lines to define the geometry of my cross-section slab. If I press Ctrl, I can continue creating my lines one after another. So if I click here and then here, create my first line, and then I continue just by continue pressing my Ctrl button, or just by clicking OK and New. For example, this is not the exact dimensions of the statement. I just need to create an example to you to follow, so you will know how to create a capture section in CivilFEM. If I go up again here and I continue creating my slab section, as here clicking in the grid, if I want to go back, I just go here, change to previous property to for each interaction, and I click here, and I finish here. So I have here all my lines. Now that I have my lines, I will create my polyline surface by curves. I can define all my lines. I can just create a box selection, and I can set here a name, bridge outline, for example, and I have my full slab bridge, but I want to create the holes, avoided the slab bridge. So I just need to create my circles. I can create a circle just here. I can set here, for example, this diameter. I know that it's very big, but you can see now. Later I can change it. For example, 35 centimeters. And I want to create the other holes, so I can use a multiple copy. I can use a vector, any line, well, following this direction. It can be this, for example, this one, and I want to set, well, the number of copies, 2 copies, and the distance between them. I can set here, for example, one meter and a half. Okay, so I have now these three ones. If I want to change them, I can modify here the other one, for example. Always I can change here the distance, and as well if I change this one, if I change the center, you will see that the rest of the circles will move as well. Okay, so if I can leave them here, okay, and then I want to well, create the voided slab. Now to subtract to make a subtraction of the full bridge, slab bridge, and subtract the holes, I will create a subtraction. So first, as always, follow these messages from the this HUD, the head-ups display. So first we select our geometric entity, and then my tools. The tools will be the voided surfaces. These ones, we can select them by the entities window or just by clicking here. Here, my three holes. Maybe sometimes it's easier to select them by the entities window or selecting it from the graphical user interface on the main graphics window, but make sure that you click on the center of gravity of each geometry. So here you have them. It's always very useful to set the names of our entities. For example, hole 1, hole 2, hole 3. Sorry. Hole 3. And my final Boolean operation, it's my voided slab, voided section. So we can, well, hide all of the auxiliary geometry, and we have my voided section. So next step is to define my material, for example C25, and then capture my section. Go here and capture this. It's already everything that we don't need is hidden, so I just select my auxiliary surface, and I set the size of my internal mesh for the section. So we have it here. Okay, here we have our section. So now I can use my section to define my beam structural element and mesh it with beam elements. And as well, if I want to perform a code checking, I can as well define a rebar and define my list of reinforcements for my cross section. In this case, I just want to I don't do that. I will just perform a typical linear structural analysis, applying just a moving load. So next step, once we have my cross section, I don't need this geometry. So well, I could delete it. Well, in this case, it's just easy as hide it, but I can delete all my auxiliary geometry because I have already defined my cross section. Now I want to define the path of my bridge. I just need to create a line, for example, from, well, following, for example, this path. I set here the layout of my bridge. and I just need to create the mesh of my bridge. Here's the layout. I just created a 15-meter bridge, and I want to, for example, model, create a beam with this layout, beam structural element, and now I want to set the number of elements. I want to create, for example, it's a 15 meters, and I want to, this case, set a length of 1 meter. If I click mesh, we'll see our beam model. It seems a solid model, but it's a beam model. If we check our geometry, it's just a line, and we assign the cross section we have defined before as a capture to this line. So we have this bridge model. So next thing is to define our boundary conditions before the creation of my moving load. So we go to loads and we define my boundary condition. I want to, well, it will be just a single nodal will fix all degrees of freedom at one end, and for the other end I will just set the movement in Y free and rotations in Z free as well. So now I want to apply my moving load. I want to apply one vertical load at each meter. For example, I want to create my load, for example, load 1. Here at my positions at 1 meter vertical, and I want to set 10 kilonewtons. Okay, here I have my first load. Well, if I hide my structural element, or I set this view, it will be easier to see the loading, and I want to place one load at each meter. I can do it well, as I have 15 nodes, as you can see here, until yeah, from node 2 to node 15. I can repeat the process 14 times, but now we want to show you another capability. It can be useful to for these processes that can be maybe can be reduced in time, and that's it. That's the using of Python commands. So first we must go to View tab and start macro recording to record all the what we in CivilFEM Python commands, everything that has been done using the graphical user interface by just clicking. So we just set here where we want to set our, for example, slab file, a Python file, and now we want to create another load, and we so everything that has been doing as always using the graphical user interface. First we create our load group, and then we define our load group, defining our direction of my loading, vertical node, vertical force, and click here, and here we have our second load group. So after defining my second load group, I can stop my macro recording as I already have enough information, and I will open my Python file. So here you can see what we have defined: the creation of the load group 2, select my node number 3, and define a vertical in a negative direction vertical force with these 10 kilonewtons of force. So if I want to create the same for the next load group, I can do it manually, as I told you, creating a lot, and I'll repeat the process for this node and this node until last node. Okay, until node 15 if you want, or use a Python file and just changing here the values for the next node. If we just copy here these commands, we can create our third load group, or we can create a loop. A loop will create all these forces in just only a few command lines. So to create a loop, we must define our loop. This is the format. Define the number of in this case we wanted to do it one by one until from the beginning. If you want to create it and well to all nodes, you want to create it 16 times from node 1 to node 16, and we must create a vector, and that vector will get the name of my load group, and I will create my load group using j as my variable. It will be iterative from 1 to 60, sorry, from 0 to 16. So here we have 15, and we will just copy and paste here in this script window. I will delete this, and I will create it using this loop in this script editor. Can be activated here in the view tab, and we create our load group here. Here you have all of them, and we can check them here. 1, 2, here until 15. Well, if you want one more, we can add at the end as well. So we have defined our moving load. Moving load separated 1 meter, and then we must solve our analysis. So to define our load cases, we can do the same. We can define one load case for each load group. In this case, I will just create 3 load cases. For load case, for example, for load case 5, for example, we will add load group number 5, and I will create another load case for case number 10, and we'll add my load case 10, and then another last load case for the last 15, and we'll add And don't forget to add always my boundary condition. Here. Here you must define one for each load group. You can define 15 load groups, load cases. In this case, you can use follow the same procedure using Python or doing manually one by one. In this case, I want to solve only 3 load cases, but you can do it for all the 15. And I just need to start solving. And now I will have, well, I can plot the real shape. Here it is. And I just need to open my load cases. So this is the load case, the first load case. Displacement here, they're very, well, in this case are very low. $15, set it in millimeters. And my last load case will be this one. I can plot another, of course, another results in bending moment. But as my results are very low, I can always multiply my using my factor, multiplying factor to my load case, and solve again. Results are obtained, and I can check now my results. Again, I have here for this case and for my last load case, I can check displacements as well in 2D or in 3D options. Okay, so in this example we have seen how to define a capture section and how to use the tool as Python to define a moving load, so we can save time in defining loads, load cases, and other things. So we go to the next example. So we will follow to the next exercise. The next exercise, well, we already have talked about it. It's about using Python commands. As you have seen before, I explained how to use Python, how to record the macros, and how to use loops and copy and paste using the script editor. So we go to the next exercise. Well, Python, you can learn more advanced Python in the Python manual, and always having the Python script commands for CivilFEM open. They are these both manuals are installed in the software. So the next exercise is how to define a simple contact pair between beam structural elements. What that can be contact pair can be defined between any structural elements. In this case, will be two beam elements. So the model is very simple. we just have defined two lines. Okay, two lines. They are separated. These two lines just 15 centimeters. There are 15 centimeters of the separation between these two lines. So the next step is to define our materials. There's only a structural steel material and cross section IPE 120. This section is assigned to both bottom and top beam. Also, the structural elements are two beam structural elements, one at the bottom and one at the top. And once it is meshed, you will see this is the load, just a vertical load applied to the tip. And to complicate a little bit this contact, we have defined we have set an orientation to the bottom beam. We have rotated this bottom beam to 20 degrees, as you can see here. So the contact is not completely flat between the bottom flange of the top beam to the top flange of the bottom beam. The bottom flange of the top beam to the top flange of the bottom beam. You can see here. And the boundary conditions are just fixed boundary conditions. Here, no, this here, and the load group will be the combination of this load and the boundary conditions. So the important thing here is to define a contact pair. How to define a contact pair is just to select to go here to mesh tab and define a new contact pair. Once we have defined it, we just have to select which will be the contacted. In this case, will be the bottom beam, and which will be the contacting structural element. As we want to be a touching contact, we just select touching contact here in the combo, as in the interaction properties part. As it's a nonlinear analysis, there's some parameters, some properties that must be set in the configuration options in the Solve tab. First of all is to activate large deflections and setting different fractions to divide this force in the different in many steps to obtain convergence. These are, and there's a contact algorithm, which is the segment to segment. So we just solve and we will obtain different results for each step. In this case, 50 steps have been solved. We open the first one and we want to monitor the one of important results in contact, which is the contact status. Always you have to, for contact results, set the scale to unity and plot results. In this case, as it's the first load, I will take out of these windows, and we will go using these buttons to go forward, so we can see how the beam start to getting closer at each step. We go, and now we can see here, if you activate the deformed shape, we can see how the bottom beam will start to deform and getting results. Here you can see another result to check this contact is, for example, the bending moment. We can check bending moment. It's better to plot them in 2D. For example, I think the contact starts at this stage, and we can plot bending moments. Here you can see the bending moment is only in a triangular shape as a cantilever, a typical cantilever bending moment shape. But once, if I plot it in 2D, the top beam is getting in contact with the bottom beam, you will see that a typical clamped beam bending moment configuration will start up to appear, as you can see here. You see, until the last one, so you see the final configuration of bending moments of the two beams. Another result is the von Mises equivalent stress. So if we open again, we can check. In this case, it's better to do it using the real shape of the beams. We will see that the bottom beam will start getting stresses. You can see here until you can see here the final configuration. And another, well, we can as well check the beams for in steel, but well, that will be in another how to define the code checking according to the standards in another webinar. So here you just that's yes, a simple example to define a contact pair between beam elements. Okay, we will go to the next part.
We want you to know that we have more CivilFEM courses. We have the International Online CAI Educational Center. There we have 3 different courses of CivilFEM powered by Marc. Every 15 days a new student enrollment is open, and the course is 3 months long from the enrollment time. You can visit the website below for further information. And we also have the International Masters in Theoretical and Practical Application of FEM and CAE Simulation. It's a unit master. It's completely online, and next enrollment is on September 2016, and it's not only for CivilFEM learning, it's also for FEM methods and theoretical application and practical application. You can visit the website below for information. That's all.